Ladies and gentlemen, welcome to our today's class. This class is a continuation on the performance of transmission line, where we discussed the nominal pi method under medium transmission. So that the example that I want us to discuss is on nominal pi method. Now, in the example, we have a 100 kilometers long, three-phase, 50 hertz transmission line has the following line constants. Resistance per phase per kilometer, 0.1 ohms. Reactance per phase per kilometer, 0.5 ohms. Susceptance per phase per kilometer, 10 times 10 power negative 6 Siemens. If the line supplies a load of 20 megawatts at 0.9 power factor lagging at 66 kilovolts at the receiving end, calculate by nominal pi method the sending end voltage, sending end current, sending end power factor, transmission efficiency, and also voltage regulation. So before we start answering the questions, let's have the equivalent circuit of nominal pi method. That will help us to analyze it very well. So on the other side, we can have the equivalent circuit where we have the line resistance, inductive reactance, and the load. Now, in our previous lesson, we discussed about the equivalent circuit of nominal pi method. And we said that the capacitance is divided into two, whereby one half is at the receiving end and another half is at the sending end. So there we have the sending end voltage. Can talk of IC1, IC2, the sending end current, the line current, and also the receiving end current. Then we also have the receiving end voltage. Now, looking at the circuit, the circuit, you can see that a half of the capacitance is lumped at the sending end and a half of the capacitance is lumped at the receiving end. So from the question, you can see that the resistance per phase per kilometer is 0.1 and the line is 100 kilometers long. So for me to now get the total resistance of the line, I'll be multiplying 0.1 times 100. Therefore, now I have total resistance per phase is equals to 100 times 0.1. That will give me 10 ohms. Total reactance per phase is equals to 0.5, that is 100 times 0.5, that will give me 50 ohms. Susceptance, the total susceptance per phase is equals to 10 times 10 power negative 6 times 100. So that will give me 10 times 10 power negative 4 Siemens. 10 times 10 power negative 4 Siemens. Now, if the line supplies a load, of 20 megawatts, that is now the receiving end power, because that's where the load is. So the receiving end power, PR, is equivalent to 20 megawatts. from the question again, you can see that it supplies 20 megawatts at 0.9 power factor lagging at 66 kilovolts. At 66 kilovolts. So this 66 kilovolts is the receiving end voltage, and the receiving end power factor is 0.9. So receiving end voltage is 66 kV. Then we have cos phi r, receiving end power factor, that is 0.9, lagging. 0.9 lagging. So we can start by getting the receiving end voltage per phase. Receiving end voltage per phase. Receiving end voltage per phase, that will be equivalent to that 66 kilovolts. 66 times 10 power 3 all over root 3. 66 times 10 power 3 all over root 3. That is receiving end voltage per phase. And when you divide that, you will be getting 38,105. 38,105.12 volts. Now, we can also go ahead and get the receiving end current. Receiving end current. Receiving end current, IR. That will be equals to the power, it is PR all over root 3 VR or root 3 VR cos phi r. So that IR is now equals to receiving end power, that is 20 megawatts. 20 megawatts, that is 20 times 10 power 6 megawatts all over root 3 times receiving end voltage. Now that I'm using root 3 here, that is the line value of the receiving end voltage. So I'll be having 66 times 10 power 3 times the power factor, which is cos phi r, and that is 0.9. So this one, when you calculate it, you will get, when you calculate that, you will get 194.39. 194.39 amperes. You will get approximately 194.39 amperes. Now we can, you remember, in our circuit diagram, you can see that cos phi r is 0.9. So if cos phi r is equal to 0.9, then it means that phi r will be the cos inverse of 0.9. Cos inverse of 0.9, and the cos inverse of 0.9 will give us, the cos inverse of 0.9 will give us 25.84. 25.84 degrees. Remember, it is lagging. That angle is lagging because you can see from our circuit diagram that the power factor is lagging. The power factor is lagging. Now, continuing on the other side, you can see, on this other side, you can see that the total resistance is 10 ohms. Inductive reactance is 50 ohms. So from there we can get the line impedance. The line impedance. So line impedance, Z is equivalent to R plus JXN, and that will be equivalent to 10 plus J50 ohms. This one is in rectangular form. Now, remember, what we have as the receiving end current is the magnitude. This is just the magnitude of receiving end current. The magnitude of receiving end current is what we have here. And this current, receiving end current, is lagging behind the receiving end voltage by an angle 25.84 degrees. So you can see that from here, we are able to get the phasor value of the receiving end current. Thus, IR in phasor, the phasor sum of IR, the phasor value of IR will be equivalent to the magnitude IR at an angle of negative phi R. It is negative because the angle phi R is lagging. It is lagging behind by 25.84 degrees. This is polar form, or we can have the same as IR into cos phi R minus J sine phi R. This will give us the value in rectangular form. So that the IR is now equals to the magnitude 194.39 at an angle of negative 25.84 degrees, which we can as well have in rectangular form. We can as well have in rectangular form. We can as well have in rectangular form as IR to be equals to, when you convert this one into rectangular, when you convert that into rectangular, it will also give us 174.95 minus J 84.73. 84.73. We can also have that in rectangular form, amperes. Now, taking the receiving end voltage as the reference phasor, we can have the current, the current, that is the charging currents, IC1. The charging current IC1, because you remember in the circuit, we cannot get the sending end current before getting the line current IL. And from here, the line current is equal to the receiving end current plus the current across the capacitance at the receiving end. So that now we can say that line current IL is equals to IR plus IC1. But IC1 is equals to, you can see that IC1 is parallel with the load. And therefore the voltage is the same. So the voltage across the capacitance at the receiving end is the same as the receiving end voltage. So I'll be having J Y over 2 times VR. Y is actually the susceptance of the line. But you can see I'm dividing the susceptance by 2 because the capacitance is divided into 2. One is at the receiving end, another one is at the sending end. So I'm dividing it into 2. So that IC1 is now equals to J, Y, that is 10 all over 2 times 10 power negative 4 times the receiving end voltage. And the receiving end voltage is 38,105.12. So this is calculated to give, J 19.05 amperes. So that now I can substitute this one into the equation for the line current. So that I have line current is equals to the load current, the load current, which is actually our receiving end current, 194.95 minus J84.73 plus J19.05. 19.05. So that is also added to give 194.95. That is this one, and then this one plus this will give us, that will give us negative 65.68 minus J 65.68 amperes. So that is in rectangular form, which we can also convert in polar form, and we get 186.87 at an angle of negative 20.58. Negative 20.58. You can see the negative is coming as a result that this, the angle should be lagging. It should be lagging. So this current IL is actually lagging because of the negative. When you convert this into polar, it will give us this. So it is a lagging, it's a lagging current. Now we can use these values. This one is in polar, is in rectangular form, and the other one is in polar form. So they give the same thing. So from there, I can now go ahead and start answering the first question. The first question that talks about the sending end voltage. And you can see now, sending end voltage, Vs is equals to Vr plus IL Z. Remember, this equation, we had seen it in our first lesson on nominal pi method. We discussed about that equation. So the Vs is equals to Vr. Vr is our reference phasor, and I said it acts as at an angle of 0 degrees. So you'll actually find that we'll use the magnitude of the receiving end voltage as it is. And remember, it is 38,105.12 plus IL. IL we already have, which I can use it in polar. That is 186. We can have, in rectangular, we have 194, 194.95, 194.95 minus J 65.68. Then the impedance, we have 10 plus J 50. So that equation is solved to give us approximately, it gives approximately 43,105, not 105, but 43,138, 43,138.93 plus J809, 0.31. Now, this is the value that is obtained by solving this. It will give us this one in rectangular form. But we can also get it in polar form, so that the Vs is equivalent to 43,891.01 at an angle of 10.62. 10.62. This one is obtained This one is obtained by converting the rectangular form into polar form. So you can now see that the magnitude of Vs, the sending end voltage, is approximately equals to 43,891 volts, which is approximately equals to 43.89 kilovolts. That is when it's converted into kilovolts, we can get that particular value. Now the sending end voltage, sending end current, not voltage, that's our question number 2. The sending end current, which we also explained in our previous class on the analysis of nominal pi, we realized that the sending end current, IS, IS is equal to IL, that is the current across the load, the line current, the line current plus the current across the capacitance at the sending end, so that we have IC2. And remember, IC2 is equals to J Y over 2 times the voltage at the sending end. Now, Y over 2 is coming as a result of the capacitance is divided into 2. And half is at the sending end, half is at the receiving end, times the sending end voltage. The sending end voltage we have obtained here. We also have Y, so we can go ahead and get IC2. That means that IC2 is now equals to J, Y is 10 times 10 power negative 4, divided by 2, into the receiving, into the sending end voltage, which we already have up here. So I can have it in rectangular form. That is 193 plus J 8090.31. So that can also be calculated. That can also be calculated. When you work it out, we can get the current across the capacitance on the sending end, and that gives us negative 4.05 plus J 21.57 amperes. 21.57 amperes. So that current is leading. And you can see that the sending end current, IS, is now equals to IL plus IC2. So we already have those values. We already have those values. So proceeding on the other page, we can have the sending end current as the line current, which we had calculated, and we got 174.95 minus J84, not 84, but it's actually 65.68. So this one was the line current, now plus the current across the capacitor on the receiving, on the sending end. That is minus 4.05 plus J 21.57. So we can break the bracket. and we can break the bracket and add to give 170.9 minus J 44.11. So this also gives us 176.5 at an angle of negative 14.47 degrees. That is IS. So you can see that the magnitude of IS equals to 176.51 amperes. Now, sending end power factor. Sending end power factor is cos phi s, and you can see that VR is our reference, Vs is leading, and Is is lagging. So Is is lagging at an angle of 14.47 degrees, and Vs is leading at an angle of 10.62. So phi s is the angle between Vs and Is. That is, by adding the two, we get 25.09. So that the power factor is equals to cos 25.09 degrees, and that gives us 0.9056 lagging. 0.9056 lagging. Now, transmission efficiency is equals to PR over PS times 100%. Now, PR is 20 megawatts. PS is equivalent to 3 Vs Is cos phi s, and that is equals to 3 times 43,891.01 times 176.5 times 0.9056. So this gives us 21.05 megawatts. And just doing it very fast, we can see that the efficiency is equals to 20 times 10 power 6 all over 21.05 times 10 power 6 times 100%. And that will give us, when you calculate that, we get 95.01%. Finally, voltage regulation. Regulation, we said, is Vs minus Vr all over Vr times 100%. And we had calculated these values we have. So you can see Vs from our calculation is 43,891.01 minus the receiving end voltage, which we calculate percent, and that gives us 15.18%. That marks the end of that calculation on nominal pi method. Now we look at more examples in our next class, and for today I want us to stop there. Otherwise, thank you and be blessed.